Hi, I'm Debra Fischer, and I am a professor in the astronomy department at Yale University. I also have joint appointments in the Department of Earth and Planetary Science, in the Department of Physics, and in the Department of Statistics and Data Science. That's one of the things I love about Yale, is that there's so much interaction between faculty and between students across disciplines. So today I want to tell you a little bit about my research, about how undergrads are involved in my work, about why I think that Yale is a unique facility, a unique opportunity, and then talk a little bit about my undergraduate courses as well. So astronomy is currently housed in these beautiful buildings on Hill House Avenue. And my research is the search for planets around other stars. I've been doing this for more than 20 years now, and so the real focus of my research at this time is the search for planets that are similar to our Earth. There are, in our Milky Way galaxy, at least 400 billion stars, 400 billion opportunities for other planets and for life in these other worlds. What's really amazing, though, is to think about what's beyond our galaxy, to get a sense of how big the universe is. 20 years ago, the Hubble Space Telescope looked at a little patch of the sky that's near the Big Dipper, the constellation, and astronomers chose this region because that part of the sky seemed very boring, dark. There weren't a lot of stars there. There didn't seem to be anything interesting going on. And so astronomers wanted to know what could be in this part of the sky. So right now I'm showing you a picture of the moon, but also a picture of the detectors that were on the Hubble Space Telescope, so you can get a sense of the angular size of the star field that Hubble was looking at. Everybody knows how big the moon is, right? So this gives you a sense of reference, a scale. Looking closer at those detectors, you can see that there are 4 overlapping detectors, 3 large ones and 1 small one. And there are a few stars that you can see in this first image that was taken by Hubble. But what was really surprising is the image that was returned after the Hubble Space Telescope looped around the Earth for the equivalent of 21 days, so about 3 weeks, opened the shutter and stared at this little patch of the sky. Hubble takes only 90 minutes to go around the Earth, so it's traveling very fast. Opening, snapping pictures, going around, opening, snapping pictures. And I would have loved to have been an astronomer at the Space Telescope Science Institute when the image came back from this part of the sky. Instead of seeing nothing, astronomers saw this: a field of galaxies. Galaxies that are too faint to be seen, even with the best telescopes of the time, right? But with the Hubble Space Telescope, because it's above the Earth's atmosphere, and this very long exposure time, adding up frames over 3 weeks of open shutter time, astronomers saw that this field contained about 10,000 galaxies. These are galaxies, collections of stars beyond our Milky Way. There's nothing unique about this part of the sky. Hubble has since looked at other patches of the sky, and everywhere Hubble looks, this is the image that we see. The entire celestial sphere is wallpapered with this kind of an image of galaxies, billions and billions of galaxies, each hosting billions of stars and billions of planets. In 1990, when I was in graduate school, we thought that most stars actually do not have planets. We thought that the solar system was unusual in having planets, this collection of planets. And if that had been the case, it would have been a logical conclusion that life is rare. But in 1995, just as I was finishing grad school, the first planet was discovered orbiting another star. And the story is really captured here on the cover of Time magazine. The question isn't a planet was found. The question was, it renewed this interest in whether or not there could be life elsewhere. Is anybody out there? So the discovery of exoplanets was seen as a step towards answering this question that so many people are curious about. The field of exoplanets, which really just started in the 1990s, launched an incredible number of research projects. NASA literally launched the Kepler spacecraft in 2009, and Kepler stared at a part of the sky, the same part of the sky, unblinking, for about 4 years, and returned images of stars and watched as planets crossed the face of the star and blocked out some of the starlight. Today we know that in fact almost every star hosts other planets. And now the question is going to be how many of these worlds are habitable or even inhabited. This is a major focus of research that I think will begin to see fruit in the next decade or 2 decades. So the first job, I think, is to try and find the planets themselves, the names and addresses. We know that the planets are there, but we have never had the sensitivity to be able to find worlds like the Earth. Here are the detections that were made with the method that I use, the radial velocity or the Doppler technique. And we've plotted up, each one of these little dots represents a detected planet. On the y-axis is the mass of the planet, and on the x-axis is the orbital period. And here you can see this little green star represents the Earth, and it looks pretty lonely there. These dashed lines represent detection limits for the radial velocity method, at least in the past. We can compare this to the discoveries that were made by Kepler. So you see that Kepler uncovered a completely different population of planets. Kepler found massive planets like Jupiter, as the radial velocity method did. But Kepler was really unique in uncovering this population of Earth-like planets, planets that are about the size of the Earth or a little bit bigger. Look how many there are. It's an incredibly dense region. You might also notice that the Earth is still out here by itself, alone, right, represented by this green star. So a planet that's the size of the Earth in a 1-year orbit these planets were not detected by Kepler. And that's because the probability of a transit scales with the distance, inversely with the distance of the planet from the star. So planets that are as far away as the Earth is from the sun have only a 1 in 1,000 chance of transiting the host star, and it's very difficult to see them because the planets are very small. So can we find Earth-like planets with the Doppler method, the method that I've been using for the last 20 years? So maybe this is longer than, it looks like it goes back 30 years to 1990. This is a picture at Lick Observatory. And this is me working on an old sun computer, trying to find planets in the basement of this telescope, working in the basement of this telescope. Since then, we found, my group and other astronomers in the world have found thousands of other planets. And the project that I'm really excited about right now is called the 100 Earths Project. So this is, my team has built a new instrument, and we're hosting it at the Lowell Discovery Telescope near Flagstaff, Arizona. We started building the instrument in about 2012, and we've now commissioned it, and you'll see we're starting to collect the first data, which look pretty exciting. In the basement in one of the buildings at Yale, we assembled the spectrograph. The spectrograph is the instrument that disperses light out into a spectrum, and then we watch the spectral lines move back and forth as the star is being tugged around a common center of mass by the orbiting planets. So this is going to be the instrument that we use to try to detect Earth-like planets. And it's an instrument that really is different from any other instrument that exists right now. I spent all of the years that I've spent working in this field, everything I learned went into improving this instrument. Here is actually first light. So Song-Hu Wang, who's one of my postdocs, was looking through the camera, and as we were projecting light, and he was staring at the optics, and the optics projected this beautiful rainbow spectrum of light on his face. So he was the first detector. You can see here we're installing the vacuum chamber for the spectrograph at the Lowell Discovery Telescope. And, the support staff were trying to show off how strong they were, right? I let them think that they were like really lifting it, but actually it was me using telekinesis to lift up this 4-ton vacuum chamber and make them feel good. Okay, and then finally my team said, all right, Deborah, get down there with a wrench in your hand and bolt down the spectrograph vacuum chamber. Pretend like you do something besides yell at us about the budget and the timeline. So I got to put in the first bolt of the vacuum chamber right into the floor of the telescope. But it was really my students who have done all of the work. So here you see the student programming some of the software in the front end module at the telescope. Here's the spectrograph, which we built at Yale and then transported down to Arizona, and it's inside the vacuum chamber, and we took this picture right before we put the last side of the vacuum chamber into place. This is a picture of the dome at the Lowell Discovery Telescope, so you can see a picture of what it looks like on a beautiful night where the sky looks like it's pretty clear. The astronomers and my students, so Rebecca went with me on an observing run, stay in a log cabin, which is just a half a mile from the telescope when we're working on our observing runs. And it's quite a lot of fun. The undergrads are running everything. They're running the instruments, they're collecting data, they're observing through the night, and they are just an absolute joy to work with. Here's the first results, right? So just for comparison, first I'm going to show you the before and the after. These are data, and it shows radial velocity, the velocity of stars that we measure, and as a function essentially of time. The data are actually phase folded, but that's a kind of detail. And you can see that, there are measurement error bars on every measurement that any physicist takes. And these error bars cause the measurements that we take to scatter. But if you take enough data, here there are something like 1,500 data points, we're able to trace out even very subtle signals, like the signal from 55 Cancri E. And in comparison, here are the data from Express, which is the spectrograph, the extreme precision spectrograph that my team built. And you can see that we need much less data because our precision is so much better. And what's really remarkable to me is to look at how this little amplitude, this very subtle amplitude, compares to the before and after. So we are on track to find more planets that are similar to the Earth. This one happens to be about 8 times the mass of the Earth, but I think we can get down to planets that are a couple times the mass of the Earth. With Express, we're setting a new standard for precision that's going to allow for detection of Earth-like planets, bringing them within reach. I also wanted to tell you a little bit about the courses that I teach at Yale. One of my favorite courses is called Origins and the Search for Life in the Universe. It's an undergrad course, and it's officially for non-science majors, although I have had some of the students in that class actually go on to become scientists. One of them just graduated from Oxford University with a PhD and worked on instrumentation there. In my class, I want the students to feel like scientists. And so here, each student has been assigned to a multi-planet system. And they carry out a simulation to understand how modeling and simulations work in science. This is, of course, a representation of the solar system, and the students are watching to see how the other planets cause perturbations in, say, the Earth or Jupiter or Venus. It's actually fascinating to see these results. And then each student is assigned a Kepler multiplanet system where they carry out the same numerical integration, and so that they can have a good understanding of the dynamical stability and the evolution of planetary orbits. Here is a course, Astronomy 255. It's a methods course in research. So one spring semester, I took some of the students down to the Arecibo telescope in Puerto Rico for fall break. And the students had prepared observing plans, and they carried out the observations, and they stayed there in the same dorms that Jodie Foster used when she was filmed in the movie Contact. I took a group of my students from the Astronomy 130 class to the Canary Islands one fall break. And we went and visited both the Mount Tidai Observatory and saw the solar spectrum, and also took geologists with us so that we could explore the geology and the volcanic activity in the region. It was a fascinating and wonderful trip. The undergrads who do research at Yale are involved in observing projects. They build instruments, they carry out data analysis, they do theoretical modeling. So here's an undergrad who's at the Keck Observatory in Hawaii. Here are the two twin Keck telescopes at 14,000 feet on Mauna Kea. We go in with everybody else on the plane who has on Hawaiian shirts. We go in with our parkas to go up to this altitude. I also took my students to the Cerro Tololo Observatory in Chile, where we built a spectrograph, which is in this telescope and is still operating today and helping with follow-up on some NASA missions. My students' prototype, these are two undergrads who worked on building a prototype of a light calibration system. We then took this design to a company and asked them to scale down the model, and we're using this system with Express for calibration of our detector. And then here are a couple of pictures. Dr. Laura Newberg is a cosmologist in the physics department at Yale. So she sent me some pictures of her students working on drones. The students build the drones, program them, and fly them over the telescopes at the Owens Valley Radio Observatory to calibrate each of the dishes. There are several telescope dishes in this array. And I think this picture, right, where all of the students, they call this, the students are being drones, right? They're acting as the drones are. You probably heard that Yale is characterized by, and. I think Yale undergrads are scientists and humanists, right? And I think here the and in Yale is science and art, research and fun, because there's just nothing like going out to these amazing sites and learning about the universe. It tells us so much about who we are. So each of these students, here's some students who all worked in my undergrad lab, and Nick and Zach and Joe and Alyssa and Charlie and AJ and Corey and Diego are all on, and Ferris are all now graduated. They've gone to law school. They work on Wall Street. They went to Caltech for graduate school. They went to Stanford Law School, Notre Dame Law School, computer scientists working for getting a PhD at Johns Hopkins University, working for Palantir, working at the Jet Propulsion Laboratories. Each one of these students forges their own path, and they're just absolutely amazing to watch what they're doing. They stay in touch with me, which is really fun. Cyril and Ted sent me an email saying, we're in Australia now, and we're looking at Alpha Centauri, and we realized that, it was 4 years ago that we worked in your lab studying Alpha Centauri, and here we are in Australia looking at the star. It takes 4 years for the light to come from the star to Earth. And so we're seeing the photons that left the star when we were working in your lab 4 years ago. Those are the connections that I really love. Those are really what Yale undergrads represent to me. Students work on research in their freshman year. They're co-authors on observing proposals and on papers. They attend observing runs around the world in Hawaii, in Chile, in Arizona. They travel to professional meetings and they present their original research. They often win prizes for their research. Ultimately, they go on to do whatever they want to do. I'm not trying to mold them into tiny astronomers. I want them to figure out what it is they want to do. So some of them will go on to graduate programs in astrophysics. They go to the best schools around the world. They may go to medical school. It's amazing to have on your medical school application that you studied astronomy. It's a great conversation starter. They go to Wall Street. They basically write their own ticket. They figure out what they want to do, and they invent new paths to take in this world. Outside of the classroom and outside of my research, I have become very concerned about climate change over the past, really watching this unfold over the past couple of decades. So with some colleagues, I co-founded a project called Astronomers for Planet Earth. You can go and visit this, and I hope that you will join us and spread the word, because climate change is a consequence of human activity. We can see the entire West Coast burning and know that this is a result of climate change. We have to stop it, and we know how. This is the great news. We know how to change things, how to reverse and mitigate climate change. It's just going to take all of us working together. Astronomers have a great, I think, vision for something like climate change on Earth. Here are some pictures that were taken of the Earth, right? Whenever we travel in the universe, we always stop and look back. So this is a picture taken from the International Space Station, which flies in a low Earth orbit about 220 miles above the surface of the Earth. This is an image taken by the Apollo astronauts when they were on the moon, so now about 239,000 miles away, looking back at the home planet longingly, I'm sure. And here's a picture of the Earth taken by the Voyager spacecraft. Voyager left the Earth in 1977 and has now traveled to the outer solar system. So looking back at the Earth, some 4 billion miles away, Voyager took this snapshot of a pale blue dot suspended in this beam of scattered sunlight. This is our planet. This is the perspective that you should have of us, our place in the universe, and our place in time as well. Astronomy gives students a perspective that they can so that they can understand that our species is amazing and unique and wonderful, and our planet is worth preserving. So my goal is to help our students discover their place in the universe and to use that so that they can improve the world, make the world a better place. Along the way, in a course like Life in the Universe, they're studying chemistry, biology, astronomy, history, and they're working on my research, which detects planets that are similar to the Earth, so that one day we can answer the question, are we alone? Thank you.